Geology, study of the composition, structure, and history of the Earth. Geology is a branch of earth science concerned with both the liquid and solid earth, the rocks of which it is composed, and the processes by which they change over time. Geology can also include the study of the solid features of any terrestrial planet or natural satellite, such as Mars or the Moon. Modern geology significantly overlaps all other earth sciences, including hydrology and the atmospheric sciences, and so is treated as one major aspect of integrated earth systematic science and planetary science. Geology describes the structure of the Earth on and beneath its surface and the processes that have shaped that structure. It also provides tools to determine the relative and absolute ages of rocks found in a given location and also to describe the histories of those rocks. By combining these tools, geologists are able to chronicle the geological history of the Earth as a whole and also to demonstrate the age of the Earth. Geology provides the primary evidence for plate tectonics, the evolutionary history of life in the Earth's past climates. Geologists use a wide variety of methods to understand the Earth's structure and evolution, including fieldwork, rock description, geophysical techniques, chemical analysis, physical experiments, and numerical modeling. In practical terms, geology is important for mineral and hydrocarbon exploration and exploitation, evaluating water resources, understanding of natural hazards, the remediation of environmental problems, and providing insights into past climate change. Geology is a major academic discipline, and it is central to geological engineering and plays an important role in geotechnical engineering. Geological materials. The majority of geological data comes from research on solid earth materials. These typically fall into one of two categories: rock and unlithified material. Meteorites and other extraterrestrial natural materials are also studied by geological methods. Minerals. Minerals are natural occurring elements and compounds with a definite homogeneous chemical composition and ordered atomic composition. Rocks. A rock is any naturally occurring solid mass or aggregate of minerals or mineraloids. Most research in geology is associated with the study of rocks as they provide the primary record of the majority of the geological history of the Earth. There are three major types of rock: igneous, sedimentary, and metamorphic. The rock cycle illustrates the relationships among them. When a rock solidifies or crystallizes from melt, magma, or lava, it is an igneous rock. This rock can be weathered and eroded, then redeposited and lithified into a sedimentary rock. It can then be turned into a metamorphic rock by heat and pressure that change its mineral content, resulting in a characteristic fabric. All three types may melt again, and when this happens, new magma is formed, from which an igneous rock may once more solidify. Organic matter such as coal, bitumen, oil, and natural gas is linked mainly to organic, rich sedimentary rocks. Tests. To study all three types of rock, geologists evaluate the minerals of which they are composed. Each mineral has distinct physical properties, and there are many tests to determine each of them. The specimens can be tested for luster, quality of light reflected from the surface of a mineral. Examples are metallic, pearly, waxy, dull. Color. Minerals are grouped by their color, mostly diagnostic, but impurities can change a mineral's color. Streak. Performed by scratching the sample on a porcelain plate, the color of the streak can help name the mineral. Hardness. The resistance of a mineral to scratching. Breakage pattern. A mineral can either show fracture or cleavage, the former being breakage of uneven surfaces and the latter a breakage along closely spaced parallel planes. Specific gravity. The weight of a specific volume of a mineral. Evanescence involves dripping hydrochloric acid on the mineral to test for fizzing. Magnetism involves using a magnet to test for magnetism. Taste. Minerals can have a distinctive taste, such as halite, which tastes like table salt. Smell. Minerals can have a distinctive odor. For example, sulfur smells like rotten eggs. Unlithified material. Geologists also study unlithified materials referred to as drift, which typically come from more recent deposits. These materials are superficial deposits that lie above the bedrock. This study is often known as Quaternary geology after the Quaternary period of geologic history. Magma. Unlithified material does not only include sediments. Magma is the original unlithified source of all igneous rocks. The active flow of molten rock is closely studied in volcanology, and igneous petrology aims to determine the history of igneous rocks from their final crystallization back to their original molten source. Whole Earth structure, plate tectonics. In the 1960s, it was discovered that the Earth's lithosphere, which includes the crust and rigid uppermost portion of the upper mantle, is separated into tectonic plates that move across the plastically deforming solid upper mantle, which is called the asthenosphere. This theory is supported by several types of observations, including seafloor spreading and the global distribution of mountain terrain and seismicity. There is an intimate coupling between the movement of the plates on the surface and the convection of the mantle, that is, the heat transfer caused by the bulk movement of molecules within fluids. Thus, oceanic plates and the adjoining mantle convection currents always move in the same direction because the oceanic lithosphere is actually the rigid upper thermal boundary layer of the convecting mantle. This coupling between rigid plates moving on the surface of the Earth and the convecting mantle is called plate tectonics. The development of plate tectonics has provided a physical basis for many observations of the solid Earth. Long linear regions of geological features are examined as plate boundaries. For example, mid-ocean ridges, high regions on the seafloor where hydrothermal vents and volcanoes exist, are seen as divergent boundaries where two plates move apart. Arcs of volcanoes and earthquakes are theorized as convergent boundaries where one plate subducts or moves under another. Transform boundaries, such as the San Andreas Fault System, resulted in widespread, powerful earthquakes. Plate tectonics also has provided a mechanism for Alfred Wegener's theory of continental drift, in which the continents move across the surface of the Earth over geological time. They also provided a driving force for crustal deformation and a new setting for the observations of structural geology. The power of the theory of plate tectonics lies in its ability to combine all of these observations into a single theory of how the lithosphere moves over the convecting mantle. Earth structure. Advances in seismology, computer modeling, and mineralogy and crystallography at high temperatures and pressures give insights into the internal composition and structure of the Earth. Seismologists can use the arrival times of seismic waves in reverse to image the interior of the Earth. Early advances in this field showed the existence of a liquid outer core where shear waves were not able to propagate and a dense solid inner core. These advances led to the development of a layered model of the Earth with a crust and lithosphere on top, the mantle below, separated within itself by seismic discontinuities at 410 and 660 kilometers, and the outer core and inner core below that. More recently, seismologists have been able to create detailed images of wave speeds inside the Earth in the same way a doctor images a body in a CT scan. These images have led to a much more detailed view of the interior of the Earth and have replaced the simplified layered model with a much more dynamic model. Mineralogists have been able to use the pressure and temperature data from the seismic and modeling studies alongside knowledge of the elemental composition of the Earth to reproduce these conditions in experimental settings and measure changes in crystal structure. These studies explain the chemical changes associated with the major seismic discontinuities in the mantle and show the crystallographic structures expected in the inner core of the Earth. Geological time. The geological time scale encompasses the history of the Earth. It is bracketed at the earliest by the dates of the first solar system material, 4.567 billion years ago, and the formation of the Earth is 4.54 billion years ago, which is the beginning of the informally recognized Hadean Eon, a division of geological time. At the later end of the scale, it is marked by the present day in the Holocene epoch. Timescale of the Earth. The following 5 timelines show the geologic time scale. The first shows the entire time from the formation of the Earth to the present, but this gives little space for the most recent eon. Therefore, the second timeline shows an expanded view of the most recent eon. In a similar way, the most recent era is expanded in the third timeline, the most recent period is expanded in the fourth timeline, and the most recent epoch is expanded in the fifth timeline. Important milestones on Earth: 4.567 billion years ago, solar system formation. 4.54 billion years ago, accretion or formation of Earth. Circa 4 billion years ago, end of late heavy bombardment, the first life. Circa 3.5 billion years ago, start of photosynthesis. Circa 2.3 billion years ago, oxygenated atmosphere, first snowball Earth. 730 through 635 million years ago, second snowball Earth. 541 plus or minus 0.3 million years ago, Cambrian explosion, vast multiplication of hard-bodied life, first abundant fossils, start of the Paleozoic. Circa 380 million years ago, first vertebrate, land animals. 250 million years ago, Permian-Triassic extinction, 90% of all land animals die, end of Paleozoic and beginning of Mesozoic. 66 million years ago, Cretaceous through Paleogene extinction, dinosaurs die, end of Mesozoic and beginning of Cenozoic. Circa 7 million years ago, first hominins appear. 3.9 million years ago, first Australopithecus, direct ancestor to modern Homo sapiens, appear. 200,000 years ago, first modern Homo sapiens appear in East Africa. Timescale of the Moon, timescale of Mars. Dating methods, relative dating. Methods for relative dating were developed when geology first emerged as a natural science. Geologists still use the following principles today as a means to provide information about geological history and the timing of geological events. The principle of uniformitarianism states that the geological processes observed in operation that modify the Earth's crust at present have worked in much the same way over geological time. A fundamental principle of geology advanced by the 18th century Scottish physician and geologist James Hutton is that the present is the key to the past. In Hutton's words, the past history of our globe must be explained by what can be seen to be happening now. The principle of intrusive relationships concerns cross-cutting intrusions. In geology, when an igneous intrusion cuts across a formation of sedimentary rock, it can be determined that the igneous intrusion is younger than the sedimentary rock. Different types of intrusions include stocks, laccoliths, batholiths, sills, and dikes. The principle of cross-cutting relationships pertains to the formation of faults and the age of the sequences through which they cut. Faults are younger than the rocks they cut. Accordingly, if a fault is found that penetrates some formations but not those on top of it, then the formations that were cut are older than the fault, and the ones that are not cut must be younger than the fault. Finding the key bed in these situations may help determine whether the fault is a normal fault or a thrust fault. The principle of inclusions and components states that with sedimentary rocks, if inclusions or clasts are found in a formation, then the inclusions must be older than the formation that contains them. For example, in sedimentary rocks, it is common for gravel from an older formation to be ripped up and included in a newer layer. A similar situation with igneous rocks occurs when xenoliths are found. These foreign bodies are picked up as magma or lava flows and are incorporated later to cool in the matrix. As a result, xenoliths are older than the rock that contains them. The principle of original horizontality states that the deposition of sediments occurs as essentially horizontal beds. Observation of modern marine and non-marine sediments in a wide variety of environments supports this generalization. Although cross-bedding is inclined, the overall orientation of cross-bedded units is horizontal. The principle of superposition states that a sedimentary rock layer is a tectonically undisturbed sequence is younger than the one beneath it and older than the one above it. Logically, a younger layer cannot slip beneath a layer previously deposited. This principle allows sedimentary layers to be viewed as a form of the vertical timeline, a partial or complete record of the time elapsed from deposition of the lowest layer to deposition of the highest bed. The principle of faunal succession is based on the appearance of fossils in sedimentary rocks. As organisms exist during the same period throughout the world, their presence, or sometimes absence, provides a relative age of the formations where they appear. Based on principles that William Smith laid out almost 100 years before the publication of Charles Darwin's theory of evolution, the principles of succession developed independently of evolutionary thought. The principle becomes quite complex, however, given the uncertainties of fossilization, localization of fossil types due to lateral changes in habitat, facies change in sedimentary strata, and that not all fossils formed globally at the same time. Absolute dating. Geologists also use methods to determine the absolute age of rock samples in geological events. These dates are useful on their own and may also be used in conjunction with relative dating methods or to calibrate relative methods. At the beginning of the 20th century, advancement in geological science was facilitated by the ability to obtain accurate absolute dates to geological events using radioactive isotopes and other methods. This changed the understanding of geological time. Previously, geologists could only use fossils and stratigraphic correlation to date sections of rock relative to one another. With isotopic dates, it became possible to assign absolute ages to rock units, and these absolute dates could be applied to fossil sequences in which there was datable material, converting the old relative ages into new absolute ages. For many geological applications, isotope ratios of radioactive elements are measured in minerals that give the amount of time that has passed since a rock passed through its particular closure temperature, the point at which different radiometric isotopes stop diffusing into and out of the crystal lattice. These are used in geochronologic and thermochronologic studies. Common methods include uranium-lead dating, potassium-argon dating, argon-argon dating, and uranium-thorium dating. These methods are used for a variety of applications. Dating of lava and volcanic ash layers found within a stratigraphic sequence can provide absolute age data for sedimentary rock units that do not contain radioactive isotopes and calibrate relative dating techniques. These methods can also be used to determine ages of pluton emplacement. Thermochemical techniques can be used to determine temperature profiles within the crust, the uplift of mountain ranges, and paleotopography. Fractionation of the lanthanide series elements is used to compute ages since rocks were removed from the mantle. Other methods are used for more recent events. Optically stimulated luminescence and cosmogenic radionuclide dating are used to date surfaces and/or erosion rates. Dendrochronology can also be used for the dating of landscapes. Radiocarbon dating is used for geologically young materials containing organic carbon. Geological development of an area. The geology of an area changes through time as rock units are deposited and inserted, and deformational processes change their shapes and locations. Rock units are first emplaced either by deposition onto the surface or intrusion into the overlying rock. Deposition can occur when sediments settle onto the surface of the earth and later lithify into sedimentary rock, or when as volcanic material such as volcanic ash or lava flows blanket the surface. Igneous intrusions such as batholiths, laccoliths, dikes, and sills push upwards into the overlying rock and crystallize as they intrude. After the initial sequence of rocks has been deposited, the rock units can be deformed and/or metamorphosed. Deformation typically occurs as a result of horizontal shortening, horizontal extension, or side-to-side strike-slip motion. These structural regimes broadly relate to convergent boundaries, divergent boundaries, and transform boundaries, respectively, between tectonic plates. When rock units are placed under horizontal compression, they shorten and become thicker. Because rock units, other than muds, do not significantly change in volume, this is accomplished in two primary ways: through faulting and folding. In the shallow crust, where brittle deformation can occur, thrust faults form, which causes the deeper rock to move on top of the shallower rock. Because deeper rock is often older, as noted by the principle of superposition, this can result in older rocks moving on top of younger ones. Movement along faults can result in folding, either because the faults are not planar or because rock layers are dragged along, forming drag folds as slip occurs along the fault. Deeper in the earth, rocks behave plastically and fold instead of faulting. These folds can either be those where the material in the center of the fold buckles upwards, creating antiforms, or where it buckles downwards, creating sineforms. If the tops of the rock units were within the folds would remain pointing upwards, they are called anticlines and synclines, respectively. If some of the units in the fold are facing downward, the structure is called an overturned anticline or syncline. And if all the rock units are overturned or the correct up direction is unknown, they are simply called by the most general terms antiforms and synforms.